Today, we'll cover code complexity metrics that every software developer should know. So in a previous video on readable code, we discussed a few metrics for measuring unreadable code. But here, we will specifically focus on code complexity. So code complexity primarily refers to the difficulty of understanding a piece of code or a piece of a code base, such as a package or module. There's also a testability aspect of it. Obviously, less complex code is easier to test. And complex code is more difficult to modify because engineers might spend considerable mental energy to understand it. And frequently, engineers will not understand the code well enough. They'll make a change, trying to fix something or add a feature, and this change will introduce a new bug somewhere else. This lack of understanding also causes another issue, and that's the fear of refactoring, because engineers don't want to refactor code that they don't understand because it may break the code base. All right, let's talk about some code complexity metrics. We're going to cover kind of four things: code style, code size, cyclomatic complexity, and cognitive complexity. So let's start with a simple one: code style. So a standard code style is definitely helpful for readability. For example, if I opened a file, saw that it had no indentation, it had really short lines, and somebody named all the variables with a leading strange prefix that I didn't understand, I would be totally confused. I'd have to stop, slow down, and read every line carefully. But if the code style was consistent, if the code style was the same from file to file across the project, I wouldn't have to pay that penalty. So the metric we want to mention is basically the number of code style violations that you have in your code base. But that said, today, most companies can enforce a code style with their CI pipeline. For example, Go programming language has a Golang CI lint, which groups a bunch of linters, including code style, that we can run on every check-in, on every merge, to make sure that things are always passing. And languages also have tools that automatically format your code to fit a certain code style, right? So code style as a metric, number of violations, really shouldn't apply anymore, except maybe for legacy projects that had a mix of code styles. With a new project, you just want to, agree on the code style or agree on a common formatter and just leave this code style issue behind you. It should not be impacting your code complexity or your readability. All right, second metric, code size. The question there is, how much code is there? The more code there is, the longer it takes to read and understand it. So this encompasses a bunch of metrics, right? It is your file size. Lines of code is another word used, and we can split it. We can say lines of code in a function, lines of code in a file, lines of code in a module or a package, lines of code in the whole code base. And so motivation for tracking these code size metrics is to help engineers split their code into kind of more manageable pieces. So one quote that I've heard from James Lewis from ThoughtWorks says about microservices that a microservice should be as big as my head. So the idea there is that one person should be able to understand the entire code base. So we can kind of split this further, right? The smaller the function is, the faster an engineer is able to understand it, right? The smaller the file is, the faster engineer is able to understand it. Smaller the packages, the smaller the code base, the faster the engineer can understand it, right? In a complex code base, it may take years, literally years, before the engineer feels like they understand the code base, right? And if we can make things smaller, right, and reduce that time to understanding, then we can ramp up faster and we can be more confident that our engineers are not going to introduce bugs because they don't understand the code base. Okay, so enough camera on me. Let's show some things. All right, so the CI-lint, so Go programming language CI-lint does have a linter for long functions. So linters are present for other languages. Also, another thing I want to mention is there's an old set of metrics called Halstead complexity measures introduced back in 1977. And one of his metrics was volume, sometimes referred to as the Halstead volume, right? And this is kind of what we're talking about when we're talking about code size. It is how much code there is. And what we talked about is like lines of code. It's a simplistic metric, but we can kind of approximate this metric, this volume, if we wanted to be kind of more specific by basically ignoring all comments and white space and then multiplying kind of the average code line length by the number of lines of code, and then we kind of get the code volume. And this approximation may be good enough for a basic complexity measure. But you have to be careful with kind of these code size metrics because people can game them, right? Here's an example. You can have a metric that says, a function length cannot be longer than 200 lines. And then suppose this is longer than 200 lines. Well, and it has a good name. Well, then the person to split it up, all they can do is just take something and then say, I'm going to refactor this into a separate method, and I would just call it do complex stuff part 2, right? So this will fit our metric of complexity metric, but it doesn't really help with readability because I just arbitrarily split this long function into 2 parts, and this name is not very descriptive, right? So just a metric by themselves is not really gonna solve your complexity issues, right? The code also has to be readable, right? You have to split the code in the right spot, and you want to name your function in a descriptive way that describes what it does. All right, so just wanted to mention that caveat. All right, let's talk about the next thing, cyclomatic complexity. So cyclomatic complexity, a very popular metric. It measures the number of linearly independent paths through a program's source code. And it is designed to uncover maintainability and testability issues. So those both two things, maintainability and testability. There's a Wikipedia article that kind of goes into more detail, but oftentimes if you go to a library that implements measuring cyclomatic complexity, it'll give you like a formula it uses. So for example, I'm going to this GoCycle library, and it tells me how it calculates complexity 1 for base complexity, and then +1 for each of these if for case, and these logical operators. So, it's fairly straightforward, and that's part of the benefit it is. It's pretty easy to understand and somewhat easy to measure. And generally what you want is, the general guidance is a score of basically 20 or less. If you want to be really aggressive, you can say you want to score 10 or less on each one of your functions. And once again, this GoCycler can be built into your linting tool. So you could add this to your CI pipeline to kind of ensure that your cyclomatic complexity doesn't rise above a certain level. All right, and finally, number 4, cognitive complexity. So cognitive complexity is a recent idea. I think I have, yep. It was introduced in 2023 by Ann Campbell from Sonar. And it basically tries to modify cyclomatic complexity by focusing on the maintainability aspect of it and not so much on the testability, right? So it focuses on the person as they're reading the code and thinks about what is more complex when a person is trying to read the code and understand it. So it basically adjusts the calculations a little bit. Let's go over a few adjustments. let's go over a few adjustments. It says, basically, it favors switches over an if-else chain. So it penalizes if-else as before, but for switches, it does not penalize them. So it kind of opinionated in that way. It favors switches. Then it makes some adjustments for logical operators, right? It basically saying that, well, if your logical operator is the same and, this is easier to understand than if you're using groups of logical operators. Then, for example, here I have to think like, oh, what's the priority of that operator? But, well, here it's like, okay, I need to meet all these conditions. Pretty straightforward. While cyclomatic complexity does not differentiate between the complexity of these two. Seems sensible. Let's go over some other stuff. Recursion, it does penalize recursion. Jump to labels, so if you do like a go-to label, it does penalize for that. Let me show you a library. So this is a Go library, Go Cognit. And it does kind of explain some of these concepts as well. Favor switch statements. Another most important point for cognitive complexity is it does penalize for nesting. Let me see. Here we go. Here's nesting. So in this example, cyclomatic complexity just does +1 for every for if statement down here. But with cognitive complexity, you will get a penalty, a +1 penalty for every level of nesting. So for example, for this for, you get a +2 penalty. While up here in cyclomatic complexity was +1, drop down another level, you get a +3 penalty. So for a small amount of code, it's possible that the cognitive complexity will be significantly bigger than your cyclomatic complexity. In general, I think people are adopting the cognitive complexity metric, starting to adopting it. People do generally agree that it's better than cyclomatic complexity. All right, so that covers kind of our 4 areas of metrics. So let's go ahead and finally, we'll talk about a few kind of tool and language specific considerations. Okay, so what I want to say first is that modern tools like IDEs and other command line tools can help with code maintainability issues. For example, you have AI tools that can index the code base and then help you explain how a piece of code or feature works, right? Obviously, this can help you with complexity because all of a sudden, because AI can understand it, the engineer does not need to spend as much of cognitive effort as they used to, right? Another important trick is IDEs can also help by collapsing or hiding boilerplate code, or perhaps reorganizing to improve their readability. Let's go and take a look at an example. Let's go back to some code, and let's write another example here. So, for example, the Go language has idiomatic error checking. So if I say error equals os read file, I'm reading some file, and then idiomatic error checking is if error is not equal to 1, then return error, or maybe return some wrapper of this error. But in either case, this kind of pattern of returning something after an error is generally pretty standard. So this is very common in the Go language. That it seems kind of silly for this to be always penalized, because like this type of code you see all the time. Another thing that the IDEs can do is they can help you hide it. So I just typed it, so it's not hiding it by default. But if I open this file, this actually would be hidden, collapsed actually by the IDE, and we can look at it like this. So it would actually look like this, all on one line, and something that you see over and over and over, so you almost don't have to think about it. So it does not add that much cognitive load to you. Another version of this is I can actually move this whole statement down here, And then this whole thing is on just one line. And a lot of people do use this pattern. So it's even kind of less code to think about. And there's other things that IDEs can do to help you. For example, if I do something like this, var I uint. So this statement up here is somewhat completely unnecessary, right? As I jump into this function, I don't actually need to worry or read about this. The fact that this is a uint only matters down here when I'm trying to use this. So one thing an IDE could do is it could completely hide this. So as you're reading this code, you don't even see this. And maybe there's like a little, different small print or something that says like this is a uint, in some way. This is just some ideas, right? And IDEs could do a lot to kind of reduce the complexity and improve readability of your code. All right. So just as a concluding statement, we discussed the major metrics: cyclomatic complexity, cognitive complexity. In our opinion, it would be nice to have a tool where the user could adjust the penalties, right? And based on their code style and internal discussions, they could decide how to penalize certain structures or certain idiomatic ways of using the language. So that way an engineering team can agree on what is considered complex code for them, for their coding experience. That's it for today.